In this next lemma 13.3, we are going to compare two topologies on a set using their bases. So let's see the statement. Here the set is X and B prime are bases for these two topologies tau and tau prime on X respectively. Then we have two statements which are logically equivalent. If any one of them is true, then so is the other. And the two statements are these. The first is that tau is coarser than tau prime, or in other words, tau prime is finer than tau. And the second statement is kind of a technical one. Let's see what it says. For each point x in X and each basis element B in B, that means this B after all is in tau, for which X belongs to B. That means it's the basis element in the topology tau which contains that point X. For them, there exists a basis element B prime in the other basis B prime, such that B prime contains the point X and is itself entirely contained in B. So if this condition is true, then this is true, and conversely if this is true, then this condition is true. So let's now see the proof. So the proof has two parts. In the first part, we prove that the second statement implies the first statement, which means that we are assuming that condition. Okay, and we are going to prove that tau is coarser than tau prime. So what should we do for this? We are going to take any element here in tau, that means an open set, and we will prove that it also belongs to tau prime. So that's why we took u in tau. And let us also take any arbitrary element x in u. Alright, now what shall we do? Where shall we go from here? Note that the topology tau is generated by the basis B, and this is an element x in u which is an element of tau. That means this u is open in tau. So by the definition of a topology generated by a basis, there will be a basis element B in B which contains that x and it's itself contained in u. Recall that this part is coming entirely from the definition of tau as the topology generated by the basis B. That is because only this type of sets U will be elements in tau for which these things happen. Alright, so we have got a basis element B which is contained in U. Okay. Now what can you do after this? Note that we now have a basis element B coming from B which contains that point X. Forget about U for a moment. Okay. Let us not think of this part that B is contained in U. You only concentrate on this part that a basis element contains the point X and it's coming from this basis. Okay. And this is where we can apply our part 2. The condition that we have in part 2 means our statement 2. So because of this, there exists the basis element B prime from that other basis. It belongs to that other basis such that it contains that point X and is itself contained in B. So this portion is coming from the second statement and the fact that we have this. Alright, but now if you see what the consequence of this is, on this, what will you get? This of course stays, but then X belongs to B prime and B prime is contained in U because it's contained in B and B is itself contained in U. So now what are you getting? You are getting the fact that for any point X in U, there exists a basis element B prime coming from this other basis which contains that point and is itself contained in U. So by the definition of the topology tau prime, which is the topology generated by the basis B prime, this U will belong to tau prime. And that's how any U which is in tau is also in tau prime. and that's how tau is coarser than tau prime, or tau prime is finer than tau. So this is 2 implies 1. Now we will prove next that 1 also implies 2. Next we go for the converse, 1 implies 2. And first we create the situation for the second statement, that means the statement 2, by taking a point x in x and a basis element b in b such that the point x is inside b. Now what do we know about the relationship between b and tau? B is the basis that generates tau. But in particular we know that b is also a part of tau. B is the subset of tau or sub collection of tau. If you take into account the fact that the elements in tau and b are after all sets. So that is why the fact that this b belongs to b will imply now that b also belongs to tau. And then you invoke the hypothesis of this converse, and the hypothesis is this, because this is the starting point now. Now we are assuming that tau prime is finer than tau. So using this containment, this then gives us the fact that b belongs to tau prime. What does this mean? It means that the set B is now open in the topology tau prime, and it contains a point x. So by the definition of tau prime as the topology generated by the basis B prime, for this open set B in tau prime and the point x inside B, there will exist a basis element B prime in the basis B prime, such that x belongs to B prime and B prime is contained in B. But that is precisely what the second statement is all about. And that's it, that's the proof. You can kind of see what is going on in this diagram. So this is your set X on which you have the two topologies tau and tau prime, and this is your set U, a subset of X which contains that point X. I didn't write anything here because you can understand that it is our point. And if this point is contained inside a basis element B coming from the basis B for the topology tau, then there exists a smaller basis element. I should not perhaps say smaller, but you get my point, okay? There exists a smaller basis element coming from the other basis which generates tau prime, which contains that point and is itself contained in this larger basis. So the finer topology tau prime, it has smaller, finer open sets that can do this type of things. They can cover points more finely than the basis elements of the topology tau can cover. You can kind of remember it in that way. So that is our lemma. And next let us see one example where now we can use this lemma to prove that the two topologies that we saw in an earlier example are actually the same. We described those topologies using some bases. Example 4. Let us recall two bases for topologies on the plane, two-dimensional plane. One of them is the collection of all circular regions in the plane, interiors of circles, and the other one was the collection of all rectangular regions in the plane, interiors of rectangles whose sides are parallel to the coordinate axis. We saw earlier that both of them are bases for some topologies on the plane. And these two topologies actually are the same, and that is that you can see from this diagram. Because if you consider the circular regions and think of their collection as your B, collection B, then you take any such circular region and think of any point in its interior. It does not matter how close the point is to the boundary, because there is some separation. So you can draw a rectangular region containing that point which is small enough so that it is entirely contained inside this. So you can think of this circular region as a basis element B in the basis of circular regions, and this rectangular region as the basis element B prime in the basis coming from the basis of all rectangular regions. So what does this figure tell you? It tells you that the topology generated by the rectangular regions is finer than the topology generated by the circular regions by our above lemma. Okay, and what about this? Instead of considering circular regions, let us first consider the rectangular regions this time. And say you take a point inside one of them, inside the interior of such a rectangle. Then again, just like this one, here also, because there will be some separation, the point is not on the rectangle itself. It is inside. It may be close to the boundary, but here in topology, close or far away, these things really do not have any sense. Although we have a distance, okay, because everything is happening in the plane, so we have an actual distance between this point and the boundary of this rectangle, but that is immaterial here. Because there is some separation, you can draw a circle small enough which will contain that point and will be entirely itself contained in the rectangular region. So what does this figure tell you? It tells you that this time the opposite is also true. This time means this is already true. Now this one is additionally telling you that the topology generated by the circular regions is finer than the topology generated by the rectangular regions. So say you name the topology generated by the circular regions C, suppose, and the other topology generated by the rectangular regions, say you call it R. Then this figure tells you that R is finer than C, and this figure tells you that C is finer than R. So combining these two containments, you get the fact that C is equal to R. So that is why those two bases generate the same topology on the plane. And we are going to use this above lemma heavily to compare topologies, which one is finer, which one is coarser, that are comparable. So let me end the video here itself. There are other things also in this section that we will see next week. So see you next week with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.